My name is Xuan Xiang, and I'm collaborating with Yao Jie, who is I'm there, and also with Bekenstein-Hawking. So today I'm talking about work on quantization of space-time based on a space-time integral operator. So we know for past 100 years, people have been pursuing the quantization of gravities by introducing new methods like for string theory, introduce string, introducing higher dimension, introduce source symmetry, or in low quantum gravity, we introduce the tetrad, etc. And in the pursuing of this theory, we find there's some strings around here. For example, for both theory, the low quantum gravity and string theory suggests there is 6 amino distance below that we cannot probe. So it acts like a UV clock. And like in Hojava deficient gravity and through a fully effective theory, Lorentz symmetry is broken as well. So we might want to ask, what if we, instead of looking at directly at the gravity theory side, if we try to construct a space-time theory based on this observation, how will we find? So our work is based on a simpler one, which is we try to construct a theory which exceeds a minimum distance. So our work is based on a previous work by Adler. So his idea is very simple. In a Riemann geometry, we know that the distance function is basically projective. So it depends on it's bilinear. So we follow the Dirac idea, so we can obtain some linear alignment instead of a quadratic alignment in terms of diagonal matrices. However, because it's a matrix, so we need some interpretation. Simplest one is to interpret it as a quantum mechanical object. So basically, we need to define something which is like expected to fail. So in Adler's idea, he suggests that we just consider a conventional non-relativistic quantum mechanics. So we define it in this way, and the epsilon is very simply just taking a complex conjugate. So we know that this is actually not Lorentz invariant. Our theory is Lorentz so it's obey Lorentz symmetry instead of the non-relativistic Galilean symmetry. So we need a new symmetry, a new way of definition of normalization. And also, in this, in the original theory, the entity of this system or this geodesic is actually depends on its eigenstate. So it depends on certain parameter. So it breaks Lorentz invariance. And also, because of this Lorentz violation, it also implies that no eigenstate actually always give you a 0 in terms of the properties measurement. And also, because as we can see, this property is defined in this way, it actually depends on the representation of these diagonal matrices. So this power distance measurement may even be complex. So we need to redefine our system such that we have a power distance measurement which is always representation independent. So we consider a very simple idea, which is we promote this coordinate difference into another operator, which is also in terms of the same relation as this gamma matrices. So in this way, our power distance measurement is relation independent. So by this reinterpretation, our theory is now actually a spin 3,1 theory. So as we all now briefly, as we know from like a Newman Harris formalism or in recent work like soft gravitons theory, we know that a spinner plays an important role in the node limit of the GR. So we may simply consider that we might try to construct a theory which just depends on spinner. So if we simply promote our space-time symmetry from a SO 3,1 to a spin 3,1, as we know, locally it's always the same, so we get nothing flexibly. However, if we promote our theory system into a quantum system, we know that global structure will affect our quantum phenomena, so we'll get something different. So simply by promoting our system action for geodesic from SO 3,1 to spin 3,1, we already get something. So to compute this quantum system, we consider a very simple generalization by considering KK ground state of a spin 3,1 worldsheet. So by considering a worldsheet, we can use fermionization to rewrite originally, which is bosonic system, and rewrite into a fermionized system by using quantization dictionary.
Where do the K-chain rule come from?
Sorry, okay, because our worksheet is cylinder. We consider a cylindrical worksheet, simple case.
Of what? Of a your series in 4 dimension or 2
2-dimension worksheet.
So you compactify a because cylinder on the torus.
On the cylinder. Yeah.
On the cylinder.
Sorry, I forget for it.
Okay.
So since for KK belongs to axial operator is vanishing, so we can write down our diaphragmatic field in terms of a single fermionized field and relate it back to our space-time bosonic object through quantization dictionary. Because we have equation state, we know it's conserved. So it means that this object is always a constant. So x is equal to quantized with a characteristic length, which is lambda. So this is the string length of our theorem. So the worldline action becomes this. Here, actually, a string length should be from length. So we arrive at a space-time integral operator by using quantization dictionary. We get this operator, which is bifermionic. And this is actually, if we check the quantization dictionary, here we can see that this is actually a discrete version of a velocity operator. So we can, of course, using this operator to define our new quadratic alignment in terms of this. So Lorentz invariant of normalization, from here we can immediately observe that we can set this lambda bar lambda equal, sorry, set up aside into constant 1, 0, and minus 1, which is kind of like normal space. So this object is quite similar to the usual spin operator in the repetitive quantum mechanical system. We know they have 3 quantum numbers, S square, SD, and density for example, electron. So in this case, we have 3, which is the time direction, the time difference, the difference in Z or Z direction, and also the volume difference. So because there's 3 quantum numbers, so we know that the total number of states is basically relative to certain part. So we know that if we apply the equation of state, this basically implies that our system is quadratic. It's relative to a set power. So it's basically saying that we have a holographic the series holographic. Also, the uncertainty are covariant, so we consider a ruler along certain direction, so we can compute the variance, and which is basically a scalar, so we know it's Lorentz invariance. And also for variance of the power distance, it is also Lorentz invariance, which is different from the previous Adler's result. So we apply equation to some very naive idea like 100 kV VGRB photon as equal to 10. So the smearing of this photon in terms of this is of order of 10 to minus 13 meter, which is negligible, as we expected. So since the Lorentz invariance is set, from here, the Lorentz everything is set, there's no destructive effect, unlike the usual double spatial relativity. Here, there's nothing, no Lorentz invariance violation. So next step is to obtain the generalized oscillating principle. So we can link Fourier mode K to the particle momentum P. But however, for Fourier analysis and spin 3.1 group, unfortunately, I do not know how to do it. So I instead of considering a full as spin 3.1, I may consider a simple one as spin 3 or rotation to SL2C. So it has been done previously by others, like Batista and Majid. So I just took their result. So let me skip this one. So basically the result is quite simple. And low energy limit is basically the usual generalized observable, which is the usual term plus the quadratic term in terms of momentum. So nothing special. So finally, that's the future work. So the next step of our work is basically try to obtain the Bekenstein-Hawking law, because we already have all the steps, so we can compute the entropy. And also, so far the model is still kinetic. There's no Hamiltonian for gravity design. So we need to add back the dynamics of the gravity part. So we can do it either incorporating loop gravity into our picture, because our picture is basically constructed on top of spin 3.1, so we can also put loop gravity into our picture, or by considering the excited states of the worldsheet action. Currently, we only consider the KK0 form, we can consider heavenmost, so we can add the gravity side. So this is the simple.
I guess we have next speaker is Wu right?
So this is.
Oh, it's you are doing the talk.
Yeah.
Oh,
and he'll give
for both